In the next kinetic vodcast of this series, we're going to take a look at half-life. What you're looking at here is the half-life of a first-order reaction. And it shows that as the time goes by, the amount of time for a reactant concentration to decrease by half is defined as its half-life. So for this pressure of this reactant CH3NC to decrease by 1/2, it takes a certain amount of time, 10,000 seconds. If you go another 10,000 seconds to here, then you're going to find that the half-life, again, which is to decrease 75 down to 37.5, is the same increment of time. So half-life is defined as the time required for 1/2 of a reactant to react. And in this particular case, we're defining that as 0.5 times the initial concentration of the reactant. When you have a situation like you see here, where the half-life is a constant value and is not changing, and the concentration of the reactant decreases in half by these regularly spaced time intervals, that's a first-order reaction. Now this equation shows how simply this can resolve down to. It goes back to an initial equation where it was concentration at a specified time divided by initial concentration. And we're going to call the time the half-life. So if you substitute these values back in and resolve them down, you get a lovely equation. It's quite simple. 0.693 over the rate constant for a first-order process will equal the half-life. And as you can see, then this reaction right here, this equation right here, there is no dependence of the half-life on the initial concentration. That's the hallmark of a first-order half-life. However, if you have a second-order process, now we have to have the inverse of the initial concentration substituted in to the initial equations that we learned for second order. This one resolves down into something that looks like this. 1 over the rate constant times the initial concentration is how you find the half-life for a second order mechanism. Now a second order reaction definitely does depend upon the initial concentration, and a second order reaction's half-life is changing and is not constant. So in this problem, sample exercise 14.9, which you will eventually copy into your PowerPoint notes, to determine the half-life of a first-order reaction, let's take a look first at the reaction they're talking about. This goes back to one previously in the chapter of butyl chloride. And from the graph, we want to first of all estimate the half-life for this reaction. So I've inserted a slide, hopefully right here, that shows our half-life. And you could probably pick any moment in time, but if we start here at 0.1, then that means half of its concentration would be at 0.05. And that time frame appears to be approximately, I'll say 350 seconds. Now if I go from 0.05 down to about 0.025, then that hopefully is somewhere at around approximately 700 seconds, which thankfully it is. So let's go back and take a look at how they solved this problem. It says on the solution, the half-life for this first-order mechanism is the time required for it to decrease to 0.05, and they came up with 340 seconds. So since it's a first-order reaction, it's simply K equals, to solve problem number B, use the half-life from the graph to calculate the rate constant. So the rate constant should be equal to 0.693 divided by the half-life. So 0.693 over 340 seconds, we get a rate constant, which by the way has the proper units for a first-order reaction, 2 times 10 to the minus 3. So that's how you could determine the half-life of a first-order reaction. And the next vodcast will begin to consider the impact of temperature on the reaction rates and specifically quantify those. Till then.